Okay, we may have accidents associated with this device, but it's a great pleasure to be here to talk to you today about aviation safety. Now, I am an applied statistician, and I know nothing, for example, about the physics of de-icing fluid or many of the things that are so important about achieving safety, let alone what might happen in the future. So I will spend my talk, which is 3 hours and 55 minutes long, mostly discussing statistics about aviation safety and answering the simple question, how safe is it to fly? Okay, now, I think Mike is going to have to help me already.
Okay, there you go.
Oh, okay. So, thank you. So the question I'll consider is, how risky is travel on scheduled passenger flights in the United States and elsewhere? But that raises an interesting question. Well, how do we measure aviation safety? And sometimes the measure that first comes to mind is not necessarily the one that's most informative. But, you know, in this age, ladies and gentlemen, in the 21st century, one gets emails from people one has never heard of. And one email, actually, I think is useful today. The person began, "My name is LS," actually had a name. "I would like to know if you, as an aviation safety expert, fly regularly. You see, I stopped flying about a year ago, and this has affected my life in a significant manner. Just one last question. What are the odds of me dying in a plane crash?" You know, someone at American Airlines said to me, well, if she doesn't fly, the answer is obviously 0. But in any case, though, I think that she was onto something. That, look, a passenger's greatest fear associated with aviation is of being killed in a plane crash, whether caused by an act of terror or by an accident. And for that reason, you might say there's a natural interest in statistics about the likelihood of that outcome. But even if you take that perspective, the question comes up, which statistics are the most informative? Now, the National Transportation Safety Board has a panoply of statistics, but one of the ones that gets quoted a lot is fatal accidents per 100,000 flight hours. And in a way, that's not a bad statistic because it's sort of like a cost-benefit ratio. The cost is fatal accidents, the benefit is flying as measured by 100,000 flight hours. But I think both the numerator and the denominator of that statistic are problematic. Why do I think that? Well, the generic term fatal accident means at least one person was killed. It blurs the distinction between a crash that kills one passenger out of 300 and another that kills 300 out of 300. Now, if we're really talking about the safety we've experienced when we fly, frankly, I'd rather be on a plane where 1 out of 300 were killed than everyone on board. Moreover, measuring activity by flying hours misses the point that most accidents occur on landing or takeoff. In fact, there have been studies by Boeing, for example, that only about 10% of the accidents, at least, occur during the cruise phase of flight. So I myself, I used to be afraid of flying, but then it got kind of boring after a while. But I remember thinking that no matter how well the flight was going, most of the risk was on the landing, which was still ahead. But that means, for example, that if you were thinking of flying to San Francisco, a nonstop flight would entail less a risk than a journey that goes Washington, Chicago, Kansas City, Denver, San Francisco. The number of flying hours might be very similar, and the number of miles covered will be very similar, but the risk associated with the increased landings and takeoffs would start to add up, okay? So then you might say, well, look, why don't you do something simple? Why not just use the ratio of passengers killed to passengers carried? That's sort of what are your odds of being killed based on the recent fraction who have been killed? And I think the statistic is worthy of respect, but there are reasons that I have been uneasy about using it. Now, some of you, you look younger than I am, most of you, almost all of you, in fact. But some of you, of the oldest of you, may remember back in 1974 when a TWA plane crashed into a mountain you know, just before attempted landing at Dulles Airport here. Any of you remember that? Mike remembers it, yeah, but even so, you must have been in your crib at the time, you know, or something. But in any case, but the point is, ladies and gentlemen, if a plane hits a mountain, killing everyone on board, it seems to me the implications about safety are the same whether the plane is completely full or 1/3 full. And yet, if we look at the number killed, it might be 150 if the plane is full, only 50 if the plane is not. In fact, you may have read just the other day, did you read about the Air France plane? A 777 in Africa, where it came close to a mountain, but fortunately the ground proximity warning devices averted any accident. There were only 37 people on board this 777. So if we looked at deaths, even if it had, God forbid, hit the mountain, you would have said that's not so many. But in terms of what it means about aviation safety, whether 37 on board or 250 seems irrelevant. Similarly, a crash that kills 28 passengers out of 28 has a very different survival rate than one that kills 28 out of 280. And if only 28 die out of 280, that might reflect excellence in emergency evacuation procedures. In other words, if we use deaths in the numerator, we might be vulnerable to irrelevant fluctuations in the fractions of seats occupied and insensitive to salient variations in the fraction of passengers killed. So you might say, are you going to go on the whole talk denouncing other metrics of safety? Well, you know, I'm from New York City, so I am negative by nature, so I could do that. But let me move on to give a statistic that I think is better, although as you will see, I don't think it's perfect. Death risk per randomly chosen flight. And basically the idea is, suppose we're talking about, let's say, Brazilian domestic flights over the 1990s. The theory is, suppose it's the New Year's Eve 1989 to 1990, you go to a party in Rio de Janeiro, and someone asks you to come into another room where there's a gigantic urn with one ball for every flight that will take place in the Brazilian domestic system over the 1990s. And you pull a ball out at random. Let's see, TAM flight 286 from Sao Paulo to Rio on March 9th, 1993. And you take that flight. What is the probability that you will not survive it for reasons related to an aviation problem? Okay? And I think that death risk per flight statistic, sort of if you pick at random in a lottery among flights, has some conceptual advantages compared to other statistics about passenger mortality risk. What are these advantages? First of all, it does ignore the length and duration of flight, which are virtually unrelated to mortality risk. You know, I think that's true if we're talking about accidents. On the other hand, to be honest, if we're talking about acts of terror, notice on 9/11 they took transcontinental flights. So I'm not positive that's true at acts of evil as opposed to pure accidents. But anyway, I think by and large it's an advantage not to consider the length and duration of flight. If you actually work out the formula, it weights each crash by the percentage of passengers killed. So if the plane hits a mountain, killing everyone on board, it counts as 100% whether the plane was full or half full. It's easy to calculate and understand because the overwhelming majority of flights don't crash at all. So all you have to do is basically work out the survival rate on the very small number of flights that actually have fatal accidents associated with them. So that is a statistic that will be the primary statistic I'll discuss today. And you might say, well, come on, you only have 30 minutes. Are you ever going to give us a number? Well, interesting that you say that. Here's a number. Let's start out the first half of the 21st century, essentially the first 8 years, 2000 to 2007. The death risk per flight, if you picked a flight completely at random among the scheduled passenger flights around the world over that 8-year period, is about 1 in 3 million. But you know, ladies and gentlemen, those of you who studied physics may remember, you remember the concept of center of mass, which is sort of the average location of the particles in a particular object. Well, you know, if you take a circular donut, the center of mass of the donut is the center of the hole, where there is no mass. Now you might say, well, that's nice to know, but how does it relate to your talk? It relates in the following way, ladies and gentlemen. Even though the worldwide average risk is about 1 in 3 million, I don't think there's one country on Earth where if I had to make an estimate based on the data for that period, I would say 1 in 3 million is the risk. Rather, that is an average of varying levels of risk. Now, I wrote a paper on the subject, which I'm happy to send you free of charge as a PDF if you simply write to me at abarnett@mit.edu. And I basically there said, well, how can we talk about the heterogeneity of risk across nations in a simple yet defensible way? And to tell you the answer, without telling you the details that went into it, but inviting you to read the paper, that it seemed that the world could be partitioned to a first approximation by a 3-population model. The safest airlines, statistically, were those that had home offices in the traditional first world. What do I mean by traditional first world? The US, Canada, most of Western and Southern Europe, Australia, New Zealand, Israel, Japan. These countries that, let's say, 30 years ago, people would have said were part of the first world. The death risk per flight statistic there was 1 in 10 million, somewhat lower than the worldwide average of 1 in 3 million. Then there was another group of countries which I classified as advancing. Some of them are countries that have entered first world status more recently. Classic examples would be Singapore and South Korea. Right now, in terms of GDP per capita, life expectancy, any of the measures, they certainly deserve first world status, but that's recent. You would not have said that 30 years ago. At the same time, there are other nations that are rapidly industrializing. Brazil is an example of such a country, but you would not yet call them first world. It turned out that as a group, they had a death risk per flight of 1 in 2 million. Interestingly, those countries that have already achieved first world status, like Singapore and South Korea, did not outperform the others that are on their way. And as I tried to explain in the paper, they did seem to form a homogeneous intermediate class. As far as the less advanced developing world, which is the other countries, most of the countries in Latin America, in Africa, many of the countries, but not all of the countries in Asia, 1 in 800,000 was the risk statistic for the period. In other words, we did have heterogeneity. Across groups, the differences in safety were of strong statistical significance. Within groups, there was no significant differences. They were within the realm of fluctuation associated with rare events. Okay? So those are the first 8 years. But now, ladies and gentlemen, I want to talk to you about the most recent 8 years, 7.4 years actually, up through yesterday. And when I sent Mike the talk, actually the night before, the 26th, I was assuming that the 27th would go safely, and I'm happy that the indications are that it did. Anyway, but so this is the most recent data, and I thought maybe instead of just giving you final numbers, maybe you should look at some of the raw numbers to get a feeling for what the pattern is like. In the traditional first world, there were 137 million flights over that period. There were 9 fatal crashes. Now, in working out death risk per flight, I take into account survival rates, but for simplicity, I just talk about the number of fatal crashes. There were 9. 11 billion passengers, 566 of whom died in aviation accidents. I believe they were all accidents. I don't believe there are any acts of terror that took lives in the first world over this period. For the advancing nations, they had 14 fatal crashes in 51 million flights, 859 fatalities, and 5.7 billion passengers. I want you to see this, ladies and gentlemen. For the least advanced countries, they had 29 million flights, 54 fatal crashes, 2,174 deaths among 2.2 billion passengers. You know, if you're looking at that, you may have, what is the fashionable phrase, cognitive dissonance? You might say, I don't get it. As you talk about flights or passengers, as you go from one category to another, the numbers are dropping off drastically, and yet when we look at fatal crashes and deaths, they're going up drastically. There's an extraordinary negative correlation here. In fact, the least advanced countries have 6 times as many fatal crashes as the first world, 54 versus 9, and yet they only have about 1/5 as many flights. So that's a factor of 6 and a factor of 5? You're saying, could that really be a factor of 30? ladies and gentlemen, these are the raw numbers. Anyway, what it turns out to happen is that in the first world, over the most recent period, the death risk per flight was 1 in 22 million, which was 55% better than the earlier 8 years in this century. The advancing nations improved to the same extent, to a 60% increase from 1 in 2 million to 1 in 5 million. So the relative risk of advancing versus first world has not really changed. They both improved to the same extent. For the less developed, actually the risk went from 1 in 800,000 to 1 in 700,000, which means collectively the countries that had the greatest room for improvement did not show improvement. The worldwide statistic was fairly stable because of these conflicting trends. Okay? I'd like to talk a little bit more, though, about the first world. And, of course, the first world, that includes us. And let me talk about how do we convey the statistics. 1 in 22 million is the most recent statistic. But if you have dealt with people who are afraid to fly, and I get a chance to do that, you know what people say? I'll be the 1 in 22 million, which, you know, sounds kind of egocentric. But the point is that what's really happening is the people are afraid of flying, and they know you're going to give them a statistic that's supposed to suggest their fears are groundless, and their defenses are up. So I was trying to think, are there ways of conveying the sheer rarity associated with 1 in 22 million? And through trial and error, I've found some things that work and some things that don't work. One thing I pointed out was, did you know that if you are in a first world airline, you're much more likely to win the jackpot in a lottery than to perish on your next flight? For example, we in Massachusetts have mass millions, where if you look at the way the lottery is conducted, your chance of winning is something like 1 in 6 million. So you could say to someone headed for Boston Logan Airport, your chance of winning the jackpot in the lottery is about 4 times as high as the chance that your next flight will end disastrously. Ladies and gentlemen, that statistic comforts no one, it turns out. I've learned. You know why? Again, you have to learn through trial and error. Deep down inside, people who play the lottery hope to win. They don't focus on how rare the winnings are. And it's not a great idea, ladies and gentlemen, to juxtapose people's best hopes and worst fears. So this statistic was of no use. You know, years ago when Jane Garvey was the administrator of the FAA and Lynn McLeod was helping her with writing speeches, Lynn would put in statistics like this in the administrator's speeches. And I once was talking to the administrator and said, you know, I don't really think that statistic works. And she said, oh, I never use it. I don't like it at all. It's in the written text, but I never say it. And her intuition was, I think, excellent because it's not a comforting statistic. Now, here's one that I think I personally find more comforting. You can have your own taste. Did you realize that at 1 in 22 million, anyone in the first world, a kid, is more likely to be elected chief executive than to perish on the next flight? Meaning in the United States, what is the chance a kid will grow up to be president? It's about 1 in 20 million. How do I get that number? Well, on average, we have a new president every 5 years based on historical data. Now we're, of course, ending the 8-year presidency of Barack Obama, but don't forget we had the short presidency of Gerald Ford, et cetera, and a number of presidencies that were even less than one full term. I think President McKinley got pneumonia in a rainstorm and only served a year. It works out to about 5 years. We have 4 million births per year in the United States, ladies and gentlemen. So over 5 years, we have about 20 million births. So for every 20 million births, we have one president elected. So 1 in 20 million would be roughly the estimate of the chance the kid will grow up to be president. That's lower than the risk of the next flight. So if you go to BWI or Reagan or Dulles and you see some kid, you know, terrorizing people, you know, with bubble gum and whatnot, and you say, this kid will never grow up to be president, well, that probably is true, but it's even less likely that the kid will experience difficulty on the next flight. Now, here's another statistic that actually does work better in terms of persuading people that flying is safe. Did you know at 1 in 22 million, if you took one flight every day, Saturdays, Sundays, and holidays included, on average, you would go 60,000 years before perishing in an aviation accident. Or even, and I even included acts of terror, so 60,000 years of perishing anyway, based on the recent statistics. Now, that number I found really does comfort some people. 60,000 years? I'm not going to live 60,000 years. Now, if you're a nasty person, you could say, well, don't forget that's an average. I mean, for some people it could be 200,000 years. I mean, for you it could be tomorrow. But the point is, though, that this statistic reminds us not only is it extraordinarily rare that any given flight will end disastrously, but even those who fly frequently, every day over a 30-year career as consultants, have a minuscule cumulative risk of dying in an aviation accident. Now, here's a statistic, actually, that I myself like. I don't know whether anyone else likes it, but let me show it to you. There was a paper I read some years ago in the journal Risk Analysis by someone from General Motors, and the title was, "Is it safer to fly or drive?" And the person said, you know, for most journeys, it's actually safer to drive. And he said that auto statistics are inflated because you have kids who are drunk, who don't put on their seatbelts, who drive cars that are poorly maintained, etc. And so if you actually look at the careful drivers, meaning people like us, and you look at their level of risk, it's really not that different from that in aviation. That, I believe, was itself not substantiated by the paper. In fact, one of the oddities of the paper was, even though for autos, he only focused on the people who are good drivers, for aviation, he threw in everything from general aviation aircraft to commercial jets and whatnot. But in any case, I thought the paper unconvincing. But I did some calculations, and you know, it's interesting. The risk of flying, when you think about it, is almost independent of distance in terms of accidents. It's basically flat, risk versus miles of flight. Whereas for driving, you would think the risk goes roughly proportional to the length of the journey, because hazards exist in every mile of the journey. Anyway, what I was able to calculate with simple numbers is that there's, if you, suppose you're thinking of going, ladies and gentlemen, from here to Chicago, and you could either drive or you could fly. Well, if you fly, you're going to save maybe 12 hours or so, okay? But ladies and gentlemen, there's a bonus. Because you flew, which is safer in terms of mortality risk than driving, your life expectancy has increased by 15 minutes. So again, you might say, well, that's not a big deal compared to the 12-hour saving, but still, it's something. I personally like this statistic. As I said, it's not portrayed on Broadway with great frequency. But in any case, the point is, ladies and gentlemen, flying is extraordinarily safe in the first world. And not only that, but let's look historically at what's happened. This is itself fascinating. In the 1960s, at the start of the jet age, the death risk per flight in first world services was 1 in 400,000. It went up to 1 in a million the next decade, 1 in 4 million the subsequent, 1 in 6 million, 1 in 10 million, 1 in 22 million. In other words, you see a continuing pattern of improvement. In fact, you know, Moore's law in terms of computer power, something about how the power doubles every certain 10 years or something. You almost have the reverse Moore's law here, that what happens statistically is the death risk per flight has dropped by about a factor of 2 every decade in the jet age, which is all the more striking because the safer it gets, the safer you might think it would get to reduce the risk even further. And yet the proportional risk has diminished by the same amount. You know, when you compare 1 in 400,000 to 1 in 22 million, that's about a factor of 60 difference. Do you ever hear there's people complaining, oh, the golden age of air travel, when people dressed up and they had filet mignon on the flight instead of spending $4 for Cheez-Its or something? But ladies and gentlemen, yes, it's true, maybe the flying was more elegant, but a factor of 60 when you think about it. I mean, yes, it was a wonderful meal, but maybe it was the Last Supper. But ladies and gentlemen, though, we have seen an extraordinary improvement. However, let me just say a few more things before IN. First of all, though, 5 minutes to go? Oh my God, I have about 50 minutes to go. Let me hurry up. Do the differences in flight risk between the first world and the rest of the world mean, given a choice, you should opt for the first world airline? I've told you that the overall statistics, the aggregate statistics are very different. But ladies and gentlemen, we have to remember something called the ecological fallacy in statistics. And a simple example would be, if I say John is better in math than Bill, I have a problem in trigonometry, therefore I should go to John. That reasoning might be fallacious because it might be that trigonometry is John's weak point and Bill's strong point. In other words, even if a pattern prevails in the aggregate, that doesn't mean it prevails in every single instance. Anyway, in the same way here, if we really want to know whether or not first world and developing world airlines differ in safety on the routes where they compete, namely from the first world to the developing world, the only way to evaluate that is to look at safety on those routes. And I have been able to do so partly because of the support of NEXTOR. I've said in other times that to find out the statistics on what flights that take place. For example, if you're going from Tokyo to Jakarta, okay, you could go on JAL or, let's say, Garuda of Indonesia. Well, to compare the safety, you have to know how many flights there are between Tokyo and Jakarta, and you have to do a certain amount of counting. That is why God created graduate students. And I had a student who worked with me, and we've done calculations, and I've been doing them for 30 years, but let me show you the answer. It's interesting. If we look at the 21st century, if you're flying between the first world and the developing world, if you fly statistically a first world carrier, your death risk per flight is 1 in 2 million, much higher than the overall risk statistic for first world aviation. However, if you fly on a carrier from the developing world country, the risk is only 1 in 2.5 million. I have seen that pattern, ladies and gentlemen, for the last 30 years, that on the routes on which first world and developing world airlines compete, there is really no difference in safety. There are aggregate differences, but on the minority of routes where they compete, those differences wither away, okay? And that, by the way, is a rule of thumb. You know, I've noticed in all looking at statistics, when you have two airlines competing on a route, very, very rarely is there a reason related to safety to prefer one of them to the other, okay? And for that matter, low-cost carriers like Southwest or EasyJet or Ryanair have safety records that are just as good collectively as the full-service legacy carriers. Two last things. First of all, I've talked about the death risk per flight statistic. It has a weakness, ladies and gentlemen. Some of you may, in the back of your mind, saying, I don't like that. And let me perhaps articulate, because it's been bothering me for a while. And that is, death risk per randomly chosen flight assumes you pick a flight at random. That's the basis of the calculation. But ladies and gentlemen, people do not pick flights at random. There are obviously far more people on an Airbus 380 than on a Beechcraft 1900, which has 19 seats. If there's any correlation of the risk of a fatal accident and the size of the airplane, all the statistics I gave you might be subject to biases. So what does one do about it? Well, finally, maybe I should have done it sooner, do the calculation both ways. In other words, if you get the same answer, then there's no point in quibbling. If you get different answers, then you have to worry more. The statistic that actually weights by the size of the aircraft, actually the simplest one is just passengers killed over passengers carried. I said last time, that I said earlier in this talk that I thought that statistic had weaknesses, but so does death risk per flight. Basically, I call it death risk per boarding. If you look at the boarding passes of all the people who flew and pick one at random, what is the probability that person would die in an accident? And what happens when we compute the statistic? It's essentially the same, ladies and gentlemen. 1 in 20 million, 1 in 7, 1 in a million. So that difference, although conceptually important, really doesn't affect the numbers very, very much. But let me say one last thing, and Mike, if it takes a moment longer, be generous. Because, ladies and gentlemen, you know, the late Joan Rivers used to say, can we talk? You know, ladies and gentlemen, I've been talking about the First World Airlines and what a great group they are, but I've wondered, maybe the US is better than the other airlines in the first world. You know, if you think about, for example, the tragic event we had earlier this year, the German wings, where there was only one person in the cockpit. Well, in the US, that wouldn't happen. Or when we read the transcript of what happened in Air France 447, when the people didn't know how to react to a stall warning and it led to the destruction of the aircraft. And then we hear about a Northwest Airlines plane that had the same problem with the pitot tubes freezing up, but got out of it safely. You might say, maybe we're better than that. We're better than the remaining airlines in that group. But here's something I think you should bear in mind. Oh, actually, there's something else we should bear in mind. Well, what's going on here? Okay. I'm going to talk about that topic in a moment. The first thing, though, I'm going to talk about is the following. Namely, I want to tell you something. You may remember, wait just a moment. I think we're having another crisis here. Wait, excuse me. Ladies and gentlemen, one more thing. I appreciate your patience. Do you remember, ladies and gentlemen, in the mid-1990s when FAA set as an objective an 80% reduction in the fatality rate by 2007? You know, at the time I thought, frankly, they were crazy. I mean, the rate was so low, how could they commit to reducing the risk by a factor of 5? Well, let's look what actually happened in the US, because we're talking about US risk now. Well, in the 1994 through 96, if we take death risk per flight, it was 1 in 2.9 million. If we look since 2007 on, it's 1 in 56 million, down by 95%. In other words, it didn't drop by a factor of 5, it dropped by a factor of 20. What if we take death risk per boarding, which I've suggested is another metric? It was originally 1 in 2.2 million. It went down to 1 in 127 million, down by 98%, a factor of 50. So I was right that they wouldn't achieve a factor of 5, but I was wrong as to why. Namely, they greatly, you people, not they, you, greatly improved it. You know, the phrase mission accomplished has suffered because of its use in it prematurely by President George W. Bush. This is a case where the mission was truly accomplished. The last thing I was saying was is the U.S. record even better than that of its compatriots in the first world? Look, to put it very briefly, if you look over the data of the 6 periods I've looked at, in 4 of them we were lower, but in 2 of them we were higher. In other words, it's not a matter of that we've consistently been higher. We've been higher or lower with the kind of random fluctuations around the mean that you would expect in a group that's homogeneous. So I think, actually, it is safer for us to describe the U.S. as a member in very good standing in the first world group, rather than to assert outright superiority in that regard. Last message, ladies and gentlemen, and I appreciate, and I apologize for going on too long. I wanted to thank you people, particularly the people at the FAA here, not the NEXTOR people, but the people at the FAA I wanted to thank for 2 reasons. The first is kind of parochial. You know, Henry Kissinger once said, academic politics is so vicious precisely because the stakes are so small. And what I think he meant was, let's say at Harvard, which is where he was on the faculty, you know, people at Harvard tend to think they should rule the world. The world is probably better off because they don't. But in their frustration that people ignore them, they have these extraordinarily bitter flights about where to put the flower pot. Ladies and gentlemen, we at NEXTOR have never been in the situation that the stakes were so small because of your generosity in giving us a chance to work on problems that really matter. You know, you have enhanced our lives immeasurably. And I thank you for myself, and I'm sure all of my colleagues at NEXTOR feel the same way. But I'd like to thank you at the end for something more universal. You know, ladies and gentlemen, it's possible, you know and I know, that people complain about the FAA and the rollout of NextGen is too slow and whatnot. But let's remember, your primary objective is safety. And you have done an absolutely spectacular job, you know, in terms of keeping things safe. You know, you may have seen, as I did, of the tragic accident in Amtrak at Philadelphia just 2 weeks ago, and how terrible it was to read. I remember one story that particularly upset me about a young boy. Did you read? He went up from Baltimore to Philadelphia with pictures of his father, who hadn't been identified. And then we learned the next day his father was one of the victims, the last one pulled from the wreckage. Ladies and gentlemen, I would suggest that there are probably thousands of people in the United States and indirectly elsewhere who are alive today who would not have been alive without the FAA's brilliant efforts. We have wonderful airlines, but believe me, my own experience is it's good that the FAA is there to remind them of the better angels of their nature, so that they achieve something that's remarkable. And for all the calls to the next of kin that were never made because of what you've done, for that I and everyone else should be thankful to you. You know, I remember, again, I'm older than most of you, I remember 1976, there was the Republican convention, and Jerry Ford at the time was up for election of president against the president to be Carter. And in his speech at the convention, he ended by saying, I hope the American people will say, Jerry, you're doing a good job. Keep right on doing it. And I was always struck by the simple eloquence of that comment, although, as we know, President Ford did not win election in 1976. Anyway, ladies and gentlemen of the FAA, you're doing a great job. Keep right on doing it. Thank you.
Thank you. It's always a challenge to follow Arnie, but thanks for the opportunity to speak here today. I'm going to talk about a project that I've been doing as part of NEXTOR with some graduate students. So this is relatively new. It's been going on for the last year or so, and it's essentially it's a safety analysis of an existing model called the Integrated Safety Assessment Model that's housed at the FAA. So some acknowledgments. This is work supported by Sherry Borner at the FAA, and we've also had a lot of support from some folks at Saab Census, and some graduate students have done most of the work that's being presented here. So the Integrated Safety Assessment Model, it's kind of a large-scale model of total risk. There's multiple types of scenarios that are considered, and it basically tries to give an estimate of risk and allows one to project changes into the model to see what the impact on risk is. And so what's kind of underlying the model is, or at least one element, is a sequence of event sequence diagrams. And so these are basically what's called an event tree. And so you have some initiating event, and so there's some initiating hazard, and then there's a series of barriers or pivoting events that attempt to keep the scenario from an accident occurring, and then there's various end states. So an initiating event could be two aircraft are on course for a near-mid-air collision, and the pivoting events could be controllers intervening to resolve the conflict. And you could have a different set of end events, such as nothing happens, near-mid-air collision, etc. And there's about 35 of these event sequence diagrams, which we'll call ESDs, and they each capture a unique initiating event, and they're categorized by phase of flight. So just to kind of give a sense of sort of the size of these models. So this is one, it's not meant to be read here, but just to get a sense of kind of what these models look like. So on the left is the event sequence diagram. The initiating event is system failure on takeoff. And then there's a series of pivoting events, and then the events on the right are the final outcomes. And generally, as you move down the tree, that's generally better. If you move to the right, it's generally worse. And also associated with these event sequence diagrams are fault trees. So a fault tree is basically a logical relationship between various components in the system, and based on if certain elements fail or work, then you get the failure or success of a particular event. So you think of the item on the left, every node has beneath it something that looks like what's on the right. So there's these set of fault trees that take things like whether the flight crew rejects it. So the end event is the flight crew rejects takeoff is one of these pivoting events, and there's a series of kind of sub-events that determine if that happens. So that's to kind of give you a sense of the size. So the model, the integrated safety assessment model, contains 35 event trees, and in those trees there's a total of 205 nodes. So each of those nodes has a probability that's populated, and then there's fault trees that are underneath the event trees, and there's about 3,500 fault tree nodes. So there's a large number, there's thousands of parameters that are in this model, and the objective, what we're given, is to identify basically the most important parameters. So one challenge is populating these nodes with data and identifying what are the most significant parameters within the model, gives some guidance in terms of where should research efforts, data collection efforts be focused in order to most improve the model. Okay, this is how some of the quantification is done, and this is so this is not what we're working on, but just to kind of give a sense of how what's in the model. So there's a lot of data on initiating events, so system failures or incursions and things like that, and then there's data on the outcomes of events, which could be accidents and fatalities or runway excursions, things like that. And there's less data on the intermediate in-between events. And so those are basically inferred. And so you have a number that's on the left, you have numbers on the right, and then you can essentially come up with numbers in the middle that basically make the beginning and the end numbers consistent. So this is just an example. So this is the first event sequence diagram, which is an aircraft system failure during takeoff. And so you see the numbers on the diamonds on the right are the end events, and the red ones correspond to some type of accident, and then the blue ones correspond to things that are safe events, so a non-accident. And so the numbers on the right come from data, and you see that there's some numbers that are zeros there, meaning that an overrun that's occurred as a result of a system failure during takeoff. There's no observed accident, and so because of the kind of the rare event nature of the data, you get some numbers that are zeros and some that are non-zeros. And so the intermediate numbers are then kind of populated to make the left and the right consistent. Okay, so the basic objective of what we've been doing is looking at some common importance measures applied to nodes that are in the model. So these are basically measures of, you take a large fault tree or an event tree, and the question is, which of these nodes really matter and which of them don't matter. Okay. And so there's a variety of metrics that are out there. These are a few examples that we've used, and you don't have to. The basic idea is you take one of the nodes and you say, if this node were to always fail, how much would the risk increase? So that would be, for example, the second metric there. You take one node, you set it to always fail, and you calculate what the overall risk would be divided by what the baseline risk is, and that's a measure that gives some indication of how significant that node is in the model. And the other metrics are sort of similar. There's kind of variations on these things. So, for example, the last one there is if you had a node and it would always work, and you look at the risk, and then you compare it to the risk when it always fails, or compare the risk when it always fails minus the risk when it always works. What is the difference? That gives a sense of how significant that particular event is within the model. So there's a variety of these kinds of things, and so when you apply these to given event trees, you get results that look something like this. So the idea is if I go back and here's an event tree. You could change the probabilities in each of these nodes and what's the outcome. So on the x-axis is basically a list of all those nodes, and then the y-axis is this importance measure. And so then you get some kind of a rank, and depending on the importance measure that's used, you would get a different ranking. And so in this particular case, so the two graphs are two different importance measures, and according to applying these two risk measures, we find that in this particular ESD that the issue of rotating and lifting off after not rejecting a takeoff is that probability is one of the critical items. And then there's some items that basically have no impact on the final result. And so we get this kind of ranking. So this is just kind of a sense of what the analysis looks like under the hood. An alternate method too that we've used. So one challenge with this is that the so we're trying to understand the most significant events. And let me go back here. So these results here are going to change if the numbers in the model are different. So they're based on baseline models. And so if you change the baseline probabilities, then the sensitivity results will change. So the question is, how sensitive, how robust are the results that are given here? And so one other method that's a little bit less sensitive to the baseline values is a full factorial analysis, which essentially tries to vary each parameter at a time. So if there's n parameters, there's 2 to the n combinations. So it's not as sensitive to the particular values that are there in the baseline. So let me just go back here and just illustrate. You might imagine, so the numbers that are zeros there, if we just let the system run for a longer time, if we had more observations, then the zeros might not truly be zeros. That there might be some risk there, and so those numbers might change as more data is obtained. And so doing the factorial design basically allows one to look at how does one factor affect the overall risk. When we look at all possible combinations, it's less sensitive to the baseline values that are used. So this is one other type of importance metric that can be applied. So this is these are in this first event sequence diagram. These are the list of the pivoting events, and we set each of them to 0 or 1, and we try all 2 to the n combinations. Then you're basically looking at the average difference, the average increase in risk when the event is set to kind of the risk, the always fail case versus the always working case. Okay, so then what happens is that we get a list, a ranking for each of these event trees. You get a ranking based on the type of importance metrics that's used. So the columns there are different types of importance metrics. So there's 2 of them that were in that initial list. There's a factorial design. There's also the factorial design also depends on how you define the upper and lower values. So there's we looked at a different set of high and low values for that particular case. And the rows are the individual pivoting events, and then the numbers are the ranks. And so what you find, and this is kind of typical in a lot of the examples, is that there's some robustness to the type of measure that's used. So what we'd hope is that if you use a different importance measure, you get the same result. That's not always the case. But what we find is that usually there's a few that kind of always show up as being important. So that's in the red there. So the C2, with the notation. So that's in this particular example, it's the capability of rotating and lifting off after not rejecting a takeoff. Maintaining control after lifting is also found to be important. And then there's some that are consistently not important. So that's the yellow there that are ranked 11th, and 10. And then there's some that are kind of in the middle that go back and forth depending on the type of metric that's used. And so the goal is to try to find, try to understand what parameters tend to consistently come up as being important versus not important. Okay. So the main observation, so we do this for basically all the 35 event trees. And the main observation is that we have similar ranks of the events from the first three, from the RAW, the Burnham importance measure, and the factorial design. So those are the first three columns. They tend to give similar ranks. It's not exactly, but if you apply this technique to all of the event trees, then you come up with generally consistent results. The main observation is that of these 35 event trees, the structure matters quite a bit. And event trees that have similar structure tend to have similar nodes in similar locations are identified as the most significant. And then again, a caveat here is that the results of the sensitivity analysis may change with different baseline event probabilities, but some of what we're doing is trying to mitigate against that by considering a number of different metrics. Okay. So here's an example of what it's a common structure. So there's a list of 4 or 5 trees. These are events that can happen on an approach, for example, an unstable approach, I think is this one. And what is identified is, so you can kind of see in the tree which elements are identified as the most significant, which is the yellow, and then the least significant is the gray. So in this particular case, what tends to be identified as important is that first event there, which is basically on the approach, does one reject the approach or not? And what's that's associated probability? And so in a way, that makes sense as being kind of a critical decision within the tree, and that comes up. It's confirmed by the sensitivity analysis. Some of the ones that are less sensitive, so that there's the gray one there, structural failure after an off-nominal landing. Essentially, whatever branch you go down from that particular node, you tend to have a similar outcome. So it does not come up as being a particularly significant item in the model. Here's another one, another type of structure. So there's a lot of event trees that have to do with takeoffs, and they all kind of have a similar, I shouldn't say they all, but a number of them have a similar structure, and so you get kind of another type of result. So you have certain nodes within the structure tend to be identified as being most significant versus others. Now, one thing to notice, this D4 here, maintaining control after failure of lifting off. So there's a few obvious reasons why some things might be identified as not being significant. In this particular case, there's 2 outcomes that are both counted as accidents, and so whether you go down the right path or the bottom path, it's at least in this initial analysis counted as an accident, and therefore the metric, the parameter is not identified as being significant with these importance metrics. So that kind of leads to so in this first analysis, the overall metric that we looked at were accidents. So there's veer-offs, excursions, things like that. They're all lumped into a category of accidents, and the analysis looked at if you change one of these parameters, how does that change the probability of an accident? And since there's different types of accidents, there's some fidelity that's lost in that type of construction. So the next thing was to consider consequence data. So the final probabilities that are identified are not with respect to accidents, but with respect to fatalities. So as you can imagine, different types of end events will have different probabilities, different fatality probabilities. And so we repeated the same analysis with looking at the sensitivity to fatalities versus sensitivity to accidents. So it's kind of a similar overall safety metric, but provides a little bit more fidelity. So here are there's similar results in the sense that categorizing the ESD trees by type of structure There's similar results for similar structure trees. But there are some differences. So this is the approach and landing structure that we saw a few slides earlier. And one thing that changes is instead of previously the most significant event was that initial decision. It was B1 is just to the left of the yellow circle there. The one to the left was previously the most significant. When you look at fatality data, it becomes the one on the right. But the other top ones and insignificant ones remain the same. And similarly, this is the other tree, and so in this case, the ones that are important and not important sort of shift around. There are differences. Before D5 was significant. Before that's the maintaining control after lifting off. The one before that was significant, and now it's dropped off. Okay, so some observations. So there's so comparing the two metrics, a fatality metric and an accident metric, and sensitivity with respect to those two metrics yields, as you might imagine, there's some similarities and some differences. So it's not I would say not a perfect match. You don't get the same results in both cases. There are similarities, but there are also some cases that have significant differences. The results within an ESD structure class are not as consistent when just looking at the fatality metric. So if you look at the when looking at the accident metric. When you look at the fatality metric, it provides a little bit more distinguishing power. So you have trees that have the same structure, and it'll identify slightly different nodes that are the most significant. So that while there is still this grouping effect, and it helps to kind of understand what's important in the models from a structure perspective, there is a little bit more distinguishing there. There are some kind of interesting observations. So, one, pivoting events located before the end event having zero fatality probability become less significant, as you might imagine. So if you incorporate a zero probability fatality number, then events prior to that will be less significant. One sort of unusual observation that has come up is that some of the events come up as having negative importance. In other words, if you make the event fail more, then the safety will improve. And some of that is because it's a rare event problem, and so the numbers in the data are, because they're rare events, there's some of these zeros, and so sometimes there's some anomalies that are some unusual things that happen, and we believe it's because you don't have a true perfect estimate of the end event probabilities. So far, what I've talked about is looking at each individual event tree one at a time, and so you take each initiating event, look at the tree, look at the next tree, and the next thing was to look at common events across the whole model. And the idea here is that there's some things that there's some nodes that exist multiple times throughout the whole model. And the question is, if we were somehow to improve those nodes, to change the probabilities, to make an individual pivoting event safer, let's say, how would that affect the risk as a whole? So this is a sort of a pictorial version here. And if you look at so there's some common events, thank you. There's some events that are duplicated, that occur, at least they're labeled the same in one event tree. So in this case, flight crew does not maintain control is listed twice here. If you go to other event trees, you have that same node that exists. Beneath that event tree are fault trees, and there are nodes in the fault tree that are listed multiple times. So some of these nodes appear dozens or hundreds of times throughout the whole model. And the question is, if you look at each of these nodes and how it affects the whole risk as the output from the model, how does that change the results? So many events are common to multiple ESDs. An event that appears multiple times, we would expect it to have a higher importance within the whole model compared to something that happens just once. Here's just a list of So the x-axis here are the event sequence diagrams. I know that they're numbered. You don't know what each one is, but I identified what a few of them are. Okay, the y-axis is the fatality probability for that particular tree. And so you see there's conflict with terrain, control system failure. So some of them are higher than others. And so the question is, how does an individual node impact what we're doing is we're summing up these probabilities. Okay. So an event that is in a tree that has a high basically has a high contribution to the sum is going to have a higher importance than a similar node in a tree that basically has a zero number that's there. So we're looking at the impact on the sum of these bars and how an individual metric would affect that. So what we do is we basically repeat the same kind of analysis and come up with a top 10 list. Do it for both fatalities and accidents. So this is an example of a top 10 list for fatalities. What's in red are nodes that come up in the top 10 list if you look at accidents. So there's some robustness here. If you repeat the analysis, you get similar results. One thing that's interesting is, so on the right-hand column is actually let me say a little bit of where these numbers come from. You take the probabilities associated with a given node increased by 1%. How does that affect the overall fatality metric of the model? Okay. So if you increase it by 1%, what's the overall change? So the numbers on the right indicate how often that particular node appears throughout the integrated safety assessment model. So you'd expect nodes that occur a lot. So the second one, the flight crew does not maintain control, which is 75 times appears in the model, that would be important just by virtue of the fact that it's in the model so often. But there's some other ones that only appear a few times that also are important. So I think there's flight crew does not detect and extinguish fire. So that only appears in one ESD, which is a fire on board the aircraft. But because it's an important node within an important event sequence diagram, it rises to the top in terms of being in the sort of top 10 overall list. So we did it for the full trees as well, but I think I should wrap up. Just a few caveats. So this analysis is all based on the assumption that the ISAM model is truth. Okay? There are some rare event data problems, as I mentioned. So the values that are the populated baseline values might not be the true values if we were to observe the system over an infinite period of time. Some of this is mitigated by considering multiple importance measures, multiple output measures, looking at individual components within the tree, looking at the system, the model as a whole. There's another assumption that common label events are treated as identical, which is something that the current in future work, basically what we're currently looking at is revisiting that assumption. Okay, so I think there's a few things to mention here. Events may be important for a lot of reasons. I guess I'll wrap up by just saying, so I think that the outcome of these results, it helps to focus research efforts, data collection efforts. What are the key things that we need data on or to understand better in terms of predicting risk? And based on how you do this analysis, you can get slightly different results, but we try to come up with some kind of robustness to the results, and I think it provides some initial indication of where to focus some of the more detailed questions that could follow. So let me stop there. I think I'm about out of time. Thank you.